Welcome to everyone. We just had a wonderful ITC colloquium by Monica Gallegos-Garcia, who joins us from Northwestern and presented results from her PhD, and she's also a Harvard Junior Fellow. And she will be the first presenter today, talking about gaining, I guess the title changed a bit, identifying the formation histories of emerging binary black holes through the mass ratio angular momentum correlation. And then we'll hear from Priyanka Sarmah, who is visiting us from the National Tsing University in Taiwan. And she will tell us about the effects of superradiance in active galactic nuclei. Then we'll hear from Giovanni Ferrami from the University of Melbourne. So we have two international speakers today. And Giovanni will tell us about the statistics of galaxy-scale strong lenses. And finally, we'll hear from Sunny Wong from UC Santa Barbara about the supernova ejecta interacting with companion stars. Go ahead, Monica.
Thank you. Like Avi mentioned, my name is Monica Gallegos-Garcia, and today I'm going to talk about some work that I've been doing to try to understand the formation histories of merging binary black holes by looking at correlations in some of their black hole properties. So sort of, for better or worse, black holes don't have too many properties. So here is just the masses of the black holes, where M1 is the mass of the primary, the more massive black hole, and M2 is the mass of the less massive black hole, and chi1 and chi2 are their spin components. So after the first 3 observing runs, the LIGO-Virgo-Cogra collaboration now has this mass distribution for the primary mass of these merging binary black hole systems. So this distribution has some interesting features. Here at around 8.5 solar masses and around 30 solar masses, there are these peaks or overabundances of detections with primary masses around those values. So one of the big questions is, what is the origin of these features? Why are they at these values versus something like 15 or 40? And what we believe is that these features in the mass distribution are a result of the physics involved with how they were formed. So in other words, there are some imprints of the astrophysics related to their formation. So ideally, we want to use these features to infer what the histories of these black holes were. So were they formed in binaries? Were they formed in dynamical environments? If it was in binaries, was it through stable mass transfer or through common envelope? So this is kind of the overarching questions that I have been asking. But instead of using something like the mass distribution, what I have been thinking about is a correlation that has been observed between the mass ratio and the effective spins of these black holes. So the mass ratio is in the gravitational wave data analysis defined as the mass of the less massive black hole divided by the mass of the most massive black hole, so it's bound between 0 and 1. And chi effective is a mass-weighted average of the spins of these black holes. More specifically, it is the mass-weighted average of the spins of the black holes in the direction parallel to the orbital angular momentum. So a spin, chi effective of less than 0 means that at least one of the components is anti-aligned with the orbital angular momentum. And then roughly 1 greater than 0 means that there is some alignment between these spin components. And the correlation that has been observed between merging binary black holes is that there is this correlation between Q and chi effective, where equal mass systems of Q close to 1 prefer to be very slowly spinning, whereas more unequal binaries prefer higher values for chi effective. There we go. So I was interested in seeing whether this correlation also appears in our binary population synthesis modeling. And to do this, I have been using Poseidon, which is a binary population synthesis code. So unlike the tools that have been used for the last 20 years, Poseidon uses grids of MESA simulations for these key phases of binary evolution. So version 1 of Poseidon is at solar metallicity, and it is publicly available, both the grids and the code. The results that I'm going to show are with version 2 of Poseidon, which is currently under development. It has a full range of metallicities that allow for this larger, more astrophysical population. But all of the results that I'm going to show here are all preliminary, so there's a big preliminary on each of these slides. So I was interested to see if with our Poseidon models we can reproduce this Q chi effective correlation that has been observed. So with the first simulation that I ran in Poseidon, I found that we do in fact have something that resembles the Q chi effective correlation. So the binary population synthesis results for the merging binary black holes that are merging locally are shown here. So this itself is intriguing and exciting to me, but I wanted to just investigate this population further. And what I found was that this larger population is actually made up of 2 subpopulations within our binary population modeling. And the differences between these 2 populations is how they were formed. So this green population that prefers equal masses and lower spin is forming through just stable mass transfer, whereas this bottom blue population are binary black holes that are forming through just common envelope. So this is pretty exciting because it's showing that we can maybe distinguish these 2 subpopulations within this wider category of binary evolution. So now what I've been trying to do is trying to understand sort of the underlying physics of both of these populations. So what about stable mass transfer and what about common envelope lead to these preferences in the Q chi effective parameter space? So if I just sort of collapse the population and just look at the chi effective values, the distribution is on the left, where again the blue is for the common envelope systems and the green is for the stable mass transfer systems. And the explanation for why common envelope is preferring these higher chi effective values is pretty straightforward and has been talked about in the literature before. And it's this, it has to do with the tidal spin up in binaries. So specifically the timescale to synchronize the star's rotation with the orbital period is a strong function of the separation of the binary. In stable mass transfer, this is a much more gradual process that doesn't lead to a lot of orbital shrinkage. So the binaries, after mass transfer, the core of the star, the core, which is the progenitor of this second black hole, is in a binary that is wide enough for them to merge within the age of the universe, or is small enough for them to merge within the age of the universe, but not small enough to be significantly influenced by the tidal spin-up. Common envelope, on the other hand, is thought to be a very efficient way to reduce the orbital separation. So this is a very efficient way to spin up the progenitor black hole through tides. So then this one would lead to a higher spinning population than stable mass transfer. So now, if we just focus on the mass ratio distribution, so I'm just showing the overall distribution as a reminder, and now we're just going to focus on the two distributions for the mass ratio itself. This is starting to seem like it involves more mass transfer physics and also some uncertainties in the common envelope prescription itself. So the story behind why this distribution looks the way it does for stable mass transfer has to do with something called mass ratio reversal. So you would rightfully, very naively expect that the less massive star in this binary will lead to the less massive black hole in the binary system. That makes sense. But sometimes these systems go through mass ratio reversal, where there is enough mass transfer from the primary star onto the secondary star that now the secondary star becomes the more massive star and leads to the more massive black hole. So now I'm plotting for this population chi-effective and their mass ratio, but now instead of enforcing that the less massive black hole is on the numerator, I'm plotting the black hole masses for the initially less massive star divided by the initially more massive star. So values greater than 1 are these systems that went through mass ratio reversal. So in gravitational waves, we can't tell which one was formed first. So what is happening is that this population is kind of folded over, and now we have something that looks more like this that prefers values closer to 1. In the common envelope scenario, it's starting to be, it seems like there's no mass ratio reversal happening, so this peak seems to be due to the process of common envelope itself, where the envelope is completely removed and all you have is the core. So I just have this last slide, which is showing that in general, we want to ask this question: are merging binary black holes formed through these big general populations, binary evolution, or dynamics? But now these results are showing that we might be able to distinguish subpopulations within these themselves. So specifically looking at correlations may be in a very robust analysis to try to see if our theory for binary evolution is correct. Thank you.
So Monica, in the law school, they teach students to argue the case of the other client. In other words, can you argue why the dynamical case would give you this correlation?
No.
Is there no explanation whatsoever?
I don't think so. So in the dynamics case, what the main result of that is that these stars or these black holes are in random trajectories everywhere. So your chi-effective distribution should be centered about 0. So this idea of your distribution sort of favoring positive chi-effective values would not work in dynamics.
What you're saying is that it will demonstrate, it will prove your case if this correlation continues.
It will prove that at least some subset are forming through this way. Right now, this doesn't currently prove any of the negative chi-effective detections. So then we would still say, well, maybe there's this correlation that I described, but on top of that, there is sort of a superposition of both of them. Yeah.
Please go ahead.
This is great. So if you go back to these slides, I think you have this other prediction for a population that was high Q and stable mass transfer phase. There's like a little wing to your, if you go, yeah. No, it's not. In the common envelope case, you have a small population. One more back. So
sorry, I'm looking at the.
That's high Q and high chi effective. Can you talk more about that?
Yeah. So again, sort of, it's a small distribution, but these are systems that, for reasons that I'm still investigating, have even tighter separations that allow for an additional sort of effects of these tides. Yeah, but these are different from the subpopulation where now they're more equal masses. So this, so it's likely that the equal mass might be is what is allowing sort of this tighter separation in some way. So I think they're working together in some way.
Is there any bias observationally why we don't see these in GW events, or is it just a small number, such as 6?
Not that I know of, because equal masses are, I think, preferred, but they look like a small population. Yeah.
Any other comment? Ramesh?
Yeah, this is really very interesting. In terms of the spin evolution, I guess your binaries all go through a tidally locked phase. So the initial spin of the star is irrelevant for these results? Or do you have to make some assumption about how stars are formed in terms of spin?
Yeah, so we assume that the 0 age main sequence stars are synchronized with the orbit. So in the very, very wide binaries, they're basically not spinning, and then very tight binaries, they are spinning, which is again this whole tide discussion.
But
yeah.
wide guys, they do go through a close phase before reaching the LIGO source population, and therefore they all get locked to the orbit.
They can, not all of them do.
Oh, okay.
So they can go through binary interactions that do shrink their orbit, but not all of them become tight enough to be tidally spun up, sort of to high magnitude.
Last question, Tony.
Oh, on your slide number 2, where you have the distribution of masses, where it drops off to the left of 8 solar masses, the errors seem small. Is that the result of lack of sensitivity in the detector, or is that really real? I mean, is it a LIGO problem that you just can't see masses that small, or there really aren't any?
Okay, I think the leading theory is that there are very few of these low masses, and they're also there's a bias towards detecting more massive ones. These types of plots are supposed to account for the biases from the gravitational wave data analysis, but there is discussion about this sort of lower end of the mass gap. Yeah, so I think that it's both physical, yeah, because this is just merging binary black holes. So here it's at 8, but it could go down to like 6 maybe, and then below that we don't, or it's unclear if there is remnants in that mass gap.
Let's thank Monica again.
Hi everyone. I am Priyanka from National Tsinghua University, Taiwan, and today I'll be speaking on my recent work on effects of superradiance in active galactic nuclei, and this work was in collaboration with Himanshu Verma, King Mathew, and Joseph Sil. Let's get started. So as you may know that the rotating supermassive black holes, it can open up a room for the ultralight scalar particles to get produced through a very intriguing phenomena known as superradiance. So superradiance, in simple words, is a phenomena where when these bosonic particles enter into the specific region of this spinning black hole, the outcome is that the exponential growth of the particles around the black hole. And this growth happens at the cost of the angular momentum of the black hole. Now the question is, if you have such a huge cloud around the black hole, where do you see it, or where do you see the effect of the fact that the black hole is losing its angular momentum? And the one signature of superradiance is the formation of depletion region in the spin versus mass plane of the black hole. So as I mentioned that because of superradiance, the black hole will spin down. So the prediction is that after spinning down, the black hole will either lie along the this critical spin curve, or they will lie below this critical spin curve. So in a way, the black holes within this region, they are getting depleted away. So hence the name goes as depletion region. So now if you observe a black hole within this depletion region, then such observation can place a bound on the possibility of existence of a particular scalar particle. Now, in absence of such observation of this depletion region, it requires precise measurement of the spin of the black hole. And such measurement is best possible when the black hole is, for example, surrounded by a luminous accretion disk. And the best example for this case is the example of active galactic nuclei, which has this supermassive black hole sitting at the core. It creates matter in the form of this accretion disk. So when you talk about superradiance in active galactic nuclei, there are mainly two key points to remember. One is that the role of accretion, which is to add mass and angular momentum to the black hole. And the other point is that now there can be two competing processes. One is that the spinning up of the black hole because of accretion, and there is the spinning down of the black hole because of the superradiance. Now in the absence of good statistics of precise spin measurements, it is worth asking a question whether can we look for ultralight scalar particles using the observable characteristics of the active galactic nuclei. So this is the question that we have addressed in our work. So before going to the details, let's have quickly know what's the condition under which this superradiance phenomenon occurs. So the condition for superradiance is that when the angular velocity of the particle is less than the angular velocity of the black hole at the horizon. And the consequence, as I mentioned, that there is a very large growth of the particles around the black hole, during which the black hole will lose its mass and angular momentum. And the black hole continues to lose its angular momentum till it reaches a critical value that can be given by this parameter alpha, known as this gravitational fine structure constant, and that is given as the product of black hole mass and the scalar mass. So now we'll first see how the whole system of the black hole and the cloud, they evolve. It evolves in the presence of a scalar field. So to know that, we solve this couple differential equation by assuming a simple accretion model, which has mainly these two parameters. One is this radiative efficiency epsilon. So this quantity, it will tell you how much of the matter of the disk is being radiated away from the disk, and how much of the matter is falling into the fate of the black hole. And the other parameter is this dimensionless accretion parameter, which is obtained by the normalizing with respect to this Eddington luminosity, which is the maximum luminosity. And then by combining these two, we get the black hole accretion rate. Then we see how the whole system evolves for the case of accreting black hole, which is shown by this red line, and for an isolated black hole shown by this blue line. And the left plot shows the spin evolution, and the right plot shows the evolution of the cloud. So you can see that for an isolated black hole, the black hole, it loses its spin and settles down at a critical value, and after that it doesn't evolve anymore. However, for an accreting black hole, you can see that once it spins down because of superradiance, now because of accretion, there will be an increase, or there will be a raise in the spin due to accretion until it reaches the next mode of superradiance, and followed by which there will be again increase in the spin. And the other striking difference between an isolated black hole and an accreting black hole can be seen in the growth of the cloud, where you can see that there is quite a boost in this cloud growth that is coming purely because of accretion. So now I'll not be focusing more on this time evolution, because the main question that we are addressing is that how the characteristics of the AGN get changed. And to know that, we start with by calculating the spectrum of the AGN using this Novikov-Thorne model that we are showing in this plot. So as you just noticed that when the black hole spins down, that is when, so we are showing this for different spin values by different colors. So as the black hole spins down, so when you go from the light blue to the dark blue, you can see that this is the lower wavelength band of the spectrum is getting squeezed. So it tells you that the higher energy photons from the accretion disk are getting depleted. And so the prediction from this spectrum is that the most prominent effect of superradiance should be seen in the higher energy bands of the wavelength, and that we exactly see in the X-ray and UV luminosity evolution that we are showing in these plots. Again, showing for the initial values, different initial values of the spin. So in this, both this evolution plots, band luminosity plots, you can see that there is this sudden drops in this time evolution, which are coming from this superradiance of the superradiance of this black hole, and this drops occurs at different time scales that correspond to different modes of superradiance, and these time scales can be further characterized by the mass of the scalar particle. So now this is the picture for when you talk about a particular benchmark point. Now the question is, how do the distribution of this black holes changes in presence of a particular scalar particle? So for that, we start with this uniform initial distribution of the black holes. So this left plot shows the evolution of the isolated black hole, and the right plot shows the evolution for the accreting black holes. Now the prediction in both these plots is that the black holes within this red curve will get depleted, and that we can see over time that as you move along time, that the black holes are getting depleted from this upper region, and then finally they are getting aligned along the boundary of this depletion region. So this is one prediction, and can see that the depletion region is more prominent for the accreting black hole case than the isolated black hole. Then the next question that we ask is that how the characteristics of the AGN get changed because of this scalar field. And to know that, we start with the same initial distribution of the mass and the spin, and first we observed that in without any superradiance, we observe this non-uniform distributions in various planes of band luminosities and Eddington ratio. However, in the presence of a particular scalar field, we observe similar kind of formation of this depletion region, which is say more prominent in the X-ray versus IR or X-ray versus UV, and the accumulation of this AGN luminosities along the boundaries of this depletion region. So the main point or the main takeaway that we want to give from this plot, or in general from overall this work, is that in the absence of a very impressive statistics of spin measurements, it is this superradiance modified relation, luminosity relation. So this superradiance modified luminosity relation can gives us a complementary probe to look for the ultralight scalar particles in the universe. So this, I'll just leave this summary to you that we observed this multiple dips in the luminosity evolution, and also we observed this formation of depletion regions along along with that we observed this accumulation of agents along the boundaries of this region in various planes of band luminosities. Thank you for listening.
Priyanka, I just wanted to, some people are not familiar with the particle physics behind what you described. I just wanted to mention that those particles have a Compton wavelength, basically the characteristic wavelength that characterizes them according to quantum mechanics, that is equal to the black hole horizon for 10 to the 8 solar masses. So these are particles that are produced because they have a wavelength that matches the size of the horizon, the ergosphere. Now, they were also proposed as dark matter for a different reason, because they are fuzzy dark matter, because in dwarf galaxies, the characteristic speed is about 10 to the minus 4 of the speed of light, so then you get 10 minus 4 squared. And so the Broadly wavelength of these particles is a kiloparsec. Instead of 1 AU, when you take the velocity to be the speed of light, it's now 8 orders of magnitude larger, which is kiloparsec. So people propose those particles as a way to solve the cusp problem in dark matter halos. And that's where your limits are important, because they can rule out a form of dark matter, right? That's the
Yes. Thank you for pointing it out. Yeah. So yes, actually the rate of this superradiance is maximum when they have the comparable size, like the horizon size is comparable with the Compton wavelength. Yes. And also these particles, these ultralight scalar particles, just have one motivation is that yes, fuzzy dark matter, and that can have other motivations come from, say, string moduli or like this. But I think for astro people, the most motivated is the fuzzy dark matter. But yes.
The last I heard is that string theory cannot be ruled out. Any comments or questions? Yeah, please.
Yeah, this is fascinating stuff, but I worry that in practice the randomness of accretion events onto the black hole could also cut the spin as a completely separate mechanism. I don't know how you would distinguish those. And variability depends on the accretion rate, which also can vary for boring astronomical reasons, nothing to do with these particles.
Okay, thank you for the question. I think the first thing that we can worry about that can also change the spin is that the emission of jets. So that we haven't really included in this work, but people have shown that this jet feedback is more prominent for the super Eddington in the super Eddington limit. So in our case, we are kind of safe because we are playing in the sub Eddington case. But however, if you walk on the super Eddington case, then yes, then there could be this two competing processes. One is this jet extraction, and other is this super radiance. So yeah, it would be interesting to see the interplay of these two processes.
I was checking while you were talking that there are roughly 10 objects with spins measured from X-ray reflection spectroscopy there. Are those useful for testing this, or would the angular momentum gained from an accretion disk, since they're high Eddington ratio objects, overcome this mechanism?
Sorry, can you just repeat?
So yeah, there are roughly 10 spin measurements from X-ray reflection spectroscopy around the 10 to the 8 solar mass range.
Yeah.
But these are all objects that are by necessity high Eddington ratio. So I'm wondering if those spin measurements are useful for you, or if you really need something that's lower Eddington ratio so that this mechanism has time to slow the black hole spin down.
Good question. So the problem working in higher Eddington ratio is that then there will be a question of the age of the agent. So and it may, because it may get dimmer, so then the age of the agent is not enough to look for this or to observe this superradiance effect, which is for supermassive black hole, which is around say 10 power 7 to 10 power 8 years or so. So that is the issue with the issue working in higher Eddington ratio case.
Okay, let's thank Priyanka.
Okay. Hi everyone, I am Giovanni. I am a third year PhD student at the University of Melbourne. I work with Mr. White on strong density statistics, and today I will talk to you about a model to estimate the strong density statistics of galaxy-galaxy scale systems. So, very briefly, to have strong lensing you need alignment, and in galaxy scale 1 arcsecond order of alignment between the line of sight of a deflector object in the middle and a background object in the back. And when you go over the scale, multiple images start to form, and there is distortion between the image of the unlensed source and what you will actually see, which is here in the bottom right. This introduces magnification of the flux that you measure for the measurement, and one of the important things of lensing is that it connects both local scale, so astrophysics, if you want, of the mass distribution of the deflector, and the global scale, so cosmology through the angular diameter distances. And you can do, again, many things. Measure the mass distribution of the deflector population. Cosmology, you can do things with the time delays or with multiple lenses systems with more than one source behind a single deflector. But many of these things have been limited by small sample statistics as of today. So this is a timeline of the discovered strong lensings of the galaxy scale. We live here about 10 to the 3. 10 to the 3 is not a precise number because a lot of those are candidates that have to be followed up spectroscopically to confirm or modeled. What is interesting is that by the end of this decade, we expect to have 10 to the 5 lenses, so 2 orders of magnitude more, thanks to Euclid, LSST, and Roman especially. To do something with this number of lenses, you need to have a grasp on how you expect the distribution to be and then infer all of that. So one way to model this is the following. So you need to account for a few key ingredients. That's cosmology. The differential comoving volume affects how at each redshift interval that the amount of lenses enter your survey. The mass function, more massive galaxies are more effective lenses because there is a larger cross-section behind them that could produce multiple images of a background source. The survey, so deeper surveys or at different photometric bands, let's say infrared, see fainter things. Fainter things tend to be farther away, and things farther away have more intervening matter on the line of sight, so it's more likely to be lensed. And finally, and importantly, is if you have 1/3 of the sky like Euclid, how you define your lensing sample, how you define them. And different methods that now have been working on neural networks or more algorithmical searches, they might have different criteria to define a galaxy to be a strong candidate versus not so much. So, and that will impact the final distribution that you see. Okay, now to get the total number of background lenses given a survey, you need, well, to find the volume behind the lens. So let's fix a lens at a given redshift and mass. Is an isothermal lens, so the mass is probed by the velocity distribution, velocity dispersion. And if you look at the caustics, so the area in which if you were to put a source, you get a multiple image, at different redshift, you can build this co-moving cone. And then you look at the source population and you model it through the lens luminosity function. So the luminosity function is the white line here. It's a Schechter function. And that gives you the co-moving density per unit luminosity. But since these are lens objects, these get magnified. So you have to account for the magnification by convolving the probability of having a certain magnification. And that's the kernel is the blue line. And what you get is the lens luminosity function, which changes mostly in the bright end. So we have a volume, we have a number density. Together you get a number, and you can integrate over the distribution of lenses, so mass distribution and redshift distribution, to get the total number of lenses per a given survey. This doesn't get you the identifiable number of lenses, so you had to add some additional constraint on what are the features that you want to look for in a given detection algorithm. For example, it could be a minimum stretch of the tangential arc of the primary image. You can account for that integrating over the lens luminosity function from different starting point in the probability of getting lensed. Similarly, the brightness of the counter image, some limits on the size. So if you have the Einstein radius, which is the scale at which the images appear, has to be bigger than the Tsing or the PSF. So ground-based surveys have a limit compared to space-based surveys. Signal-to-noise ratio, or visibility through the lens light. And since I'm using isothermal lenses, there is a relation between where the images appear and the magnification. So you can sample the deflector population through the fundamental plane, estimate the surface brightness at the position where the images appear, and compare the two, and see what fraction of those can be seen. And well, the outcome is something like this. You can get a distribution of redshifts on the left. The solid line is the deflector population. The source population is dotted. And on the right is the Einstein radius distribution. I plotted here 4 different surveys, Roman, LSST, DES, and one specific field of JWST. So just to point a couple of things, for example, DES is ground-based, is not as deep as other surveys. It tends to see lower redshift distributions and is limited to settings only bigger than 1 arcsecond. While JWST is infrared, you see higher redshift, it's much deeper, and it's in the sky, so you can see the full distribution of Einstein radii. On the top right is the number of lenses you expect for each survey. Of course, JWST is very small. You expect about order of 8, 10 lenses. And you recover the 10 to the 5 that you expect for the other surveys. I then, well, you can do a few things now while you wait for the end of the decade, is to test it on a smaller field. So I then looked at the JWST field to see what I can find. And I have order of 10 so far. I have been working on this, so look at following up with redshift and models. You can see that, for example, the distribution of redshift compared to a ground-based survey allows you to probe a different area, so higher redshift of the lens and the deflector and the source. I've been working with V, trying to characterize the AGEL survey, which is a follow-up on the DES, a search of lenses in the DES field. And if you, this is a spectroscopic follow-up. So if you account for the fact that you can only see in certain band of the infrared for the source population through the atmosphere, you are limited to this region, and that describes pretty well the observations so far. Finally, you can, if you have a model that can be tuned in the inputs versus the output, you can, in a way, do the inverse problem. So, and this is a work in progress. idea is that if you trust your sample of lenses, you can say, okay, which is the best mass function? In this case, the velocity dispersion function is a tracer for that describes the best sample. So here is the velocity dispersion function and some way to parameterize it with redshift. So I'm changing the normalization and the scale velocity. And this is the way that the lensing observables change by changing these two parameters. So with this, there is an additional problem. So the idea that you can do this comes from the fact that the velocity dispersion entering the isothermal model has been found by many different studies to match, on average, the velocity dispersion of the stellar component. So if you measure the velocity dispersion through the stellar component at actually 0.5 to 1, which is where the lens spin population lives, you get the yellow line. And if you infer it through lensing, this is a work through Chai 2010, you get the blue line. And they tend to match at low sigmas, but not so much at high sigmas. So one way to account for it is to include the scatter in the distribution. And I use the SL2S sample. And if you include the scatter, again, is a convolution effectively on these two to map from the lens, isothermal lens sigma to the velocity dispersion sigma of the stellar component. So I did it for 5 fiducial ones, and you have to deconvolve it first, do the lensing estimation, and then convolve it again to match it with the stellar component. And that's the result. It seems to cancel out the tension at high sigmas. And yeah, that's it for me. And I'll leave you with a couple of the relevant papers I did with Stu. Thank you.
The Webb telescope detected, as you know, galaxies up to redshift 16.
Yeah.
What is the optical or the lensing probability for those? Did you check?
It flattens out pretty much. So you're talking about what people refer as tau, multiple image optical depth. I remember checking for redshift 10, and it's still about 1 every 200 to 1 every, about 1%. It shouldn't change that much if you go farther away. And especially these single deflectors, they are, have lower maximum magnification usually, so they're harder to push to that high redshift in general. No, they shouldn't.
Ramesh?
Yeah, so you're trying to describe your whole lensing model in terms of just the velocity dispersion. That looks like a spherical model, but you showed an asteroid costing, for which you need actually an anisotropic lens.
Yeah.
So in your model, do you include anisotropy? And if you haven't, do you think that will change some of the results?
I do include it. So
Then how do you choose?
So,
say ellipticity.
I use a singular isothermal ellipsoid for the model, and I draw from a distribution, a measured distribution, which is from Van der Velde, I think, based on SCSS, at the redshift interval where the lens lives. So I think the mean is 0.7 as the axis ratio. And that changes, the area and the probability of getting things quadruply lens versus doubly lens. And yeah, that's accounted for. Yeah.
Does it really make a difference? Because this has always confused me.
So
whether overall integrated, it's almost the same, or does it make a big difference?
It changes by 10% the area within the overall caustic, which it's a difference. And then again, you can
maximum magnification will be, I think, different.
Yeah, the maximum magnification is still a power law at especially the high end. So then if you introduce extended sources, that get cut off anyway. So it's a bit degenerate between the two things.
Yes.
May I ask a question? So first of all, it's a clarification question. So in the second plot here, are you showing the solid line for the length redshift and also the dashed line for the source redshift?
Yes.
Okay, so if that's the case, with generality, why the source redshift is not that high compared with ground-based observation? Because like generality has the power to detect things at an even higher redshift. In principle, the isolated radius should be larger for source redshift.
Well, the isolated radius, again, the isolated radius is a function of the ratio of the angular diameter distances. So at some point it flattens out, but on top of that, you have to account for the evolution of the source population. So yeah, I'm drawing from the luminosity function, and the luminosity function goes down with redshift normalization. So the interplay between the two things lead to this.
So basically, that's because of the source density jump off.
Yeah.
Yes. What happened if we have like two lenses that looks close enough in our line of sight that looks like one lens that can really differentiate from one
Small
lens
probability,
versus two
it's
lenses?
1%.
With like the lensing effect, can we differentiate?
So you mean
If we have like two lenses that are close enough along a line of sight that it looks like one object due to observation?
So that double lensing, let's say.
double lensing? Okay, double lensing should be, I guess, one way to estimate is sort of Poisson statistics of having two things along the same line of sight. So it should be, again, 1% of the number of lenses that are single lenses. You can correct for that because the caustic shape changes a bit by the second object in the line of sight. Shouldn't change much. And it should change if you do, and that's what we see in AGEL, for example, is that if you select things in a lower resolution thing like DES, and then you follow up with Hubble's telescope images, then you have a different probability of seeing because you're already selecting big Einstein radii, so they are more effective deflectors, so it's more likely to see a second object. But yeah.
But with 10 to the 5 lenses, you might have a few that
Yeah.
belong to that. So that would be interesting.
Yeah, I estimated 500.
500.
Yeah.
Wow. Yes.
Well, one thing that's coming real soon now is a measurement of lensing everywhere on the sky, because the microwave background polarization the lensing converts E mode into B mode, and so any arc minute scale B mode is definitely lensing, and that can nowadays be detected at about a 50 sigma level. And so you can measure at every point in the sky the amount of lensing.
So that's mostly weak lensing at that scale, and so in a way it's a simpler model in the sense that you are less affected by a lot of the astrophysics at the scale, but that changes the way that you should sample the deflector population, and so probably that you want to study instead of velocity dispersion function, the halo mass function, and it's a bit of a like you probably can tune this to account for that, but it's a bit of a different ingredient in the model, I think, because it's a scale.
Large scale structure as well.
Yeah.
With lensing, so it's a different calculation.
Yeah. That's interesting.
Okay, if no more questions, let's thank
Okay, so hello everyone. I'm Sunny Wong. I'm a 6th-year graduate student from UC Santa Barbara, working with Large Spilston, and I'm generally interested in using binary models to look at white dwarfs in the binary and their role as progenitors of type 1a supernovae. And today I'll show you some of our recent results of a type 1a supernova ejecta interacting with a white dwarf companion. So type 1a supernovae can be used as standard candles, which allows us to measure precise distances to galaxies. And this allowed us to discover that the universe's expansion is accelerating. But despite their important roles, type 1a supernovae still has a good number of mysteries, including how they form exactly. So most theories now agree that type 1a supernovae come from thermonuclear explosions of a carbon-oxygen white dwarf. And most theories would agree that this comes from some kind of binary interaction. So this carbon-oxygen white dwarf is accreting mass from some companion, but we don't really agree on what the nature of this binary companion is. So is it a main sequence star like our sun? Is it a red giant? So for the rest of today, I will focus on a case where the binary companion is another white dwarf. So either a helium white dwarf or another carbon-oxygen white dwarf. Now, the very special thing about this double white dwarf scenario is that a white dwarf is very compact. One solar mass white dwarf is around the same size as the Earth. So in order for the binary companion to be filling its Roche lobe and start transferring mass, the binary orbit has to be very tight. We're talking about binary separations of order a few Earth radii and orbital periods of order a few minutes. So the binary would have orbital velocities of 1,000 to 2,000 kilometers per second. Now, the exploding white dwarf, after it explodes, the binary is unbound, and so that would leave the companion star flying off at its orbital velocity around 1,000 to 2,000 kilometers per second. So a solid prediction of the double white dwarf scenario would be that there should be high proper motion objects in the sky. And so with Gaia DR2 and DR3, we now have 7 such hypervelocity candidates. These are some of the fastest moving objects in the Milky Way galaxy, and they will actually leave the Milky Way in a couple million years. So the plot on the right here shows their inferred ejection velocities and their distances in the red and blue points here. So all of these lie upwards of 1,000 kilometers per second, consistent with the prediction of the theory. And on the plot on the left here shows where they are on the Gaia color magnitude diagram. So again, focus on the red and blue points. So all of these objects lie between the main sequence and the white dwarf sequence. What that means is that these objects have puffed up by a factor of 10-ish. And I will show you some simulations to show how we understand how these become so puffed up. And for the rest of this talk, I want to focus on this red point here. This object has the most well-constrained orbit ejection velocity, and its name is D62. So from the ejection velocity, we can infer what its mass is by the following procedure. So a white dwarf has a very distinct mass-radius relation because they're electron-degenerate objects. A less massive white dwarf is actually larger in radius. And so if you assume that the star is filling its Roche lobe, then a low-mass white dwarf would have a wider orbit, and along with it, a lower ejection velocity. So the relatively low ejection velocity of D62 of around 1,000 kilometers per second allows us to infer its mass to be around 0.1 to 0.2 solar masses, which puts it in the range of a helium white dwarf. The other very special thing about D62 is that if you trace its trajectory back by around 10 to 5 years, in the blue lines here, it actually nicely coincides with a known supernova remnant. So if you assume that this remnant came from the same explosion that produced D62, this gives us a nice age constraint around 10 to 5 years. So we want to know how D62 came to be so big and puffy, and so we do hydrodynamical simulations with the Athena++ code to study how a helium white dwarf donor would interact with the supernova ejecta. So we put in the donor star into the grid, and then we shock it with a supernova ejecta of around 1 solar masses and a typical kinetic energy of around 10 to 51 ergs. That's a typical value for a type 1a supernova. And we now look at how the donor star puffs up. So I will show some of our movies. There are 2 panels here. The left panel shows the fraction of material that's coming from the donor star. The yellow stuff is the donor, and you will see blue stuff coming in from the left side. That's from the ejecta. And the right plot here shows the density. Okay, so now you see the ejecta coming in from left side, and as it goes around the donor, there's a bow shock around it. And also because it has to go around the donor star, there's a low density wake behind the donor with half an opening angle of around 30 degrees. So it would be interesting to see whether this asymmetry in the supernova ejecta persists when it enters the remnant stage. The other thing I want to highlight is that on the plot on the left here, you see some yellow material from the donor getting stripped off and going along with the ejecta. this material is unbound and which might have detectable consequences. I will now show you kind of assumed inversion of the movie, focusing on the donor star. So the ejecta is coming in at around 10,000 kilometers per second, which is a lot of kinetic energy. And as it runs through the donor star, it sends a shock wave into the center of the donor and depositing heat into it. Now, after the donor gets shocked, it rapidly expands to larger sizes. Okay, so if you ask where does the unbound material from the donor star lie, we find that typically the donor loses around 0.01 to 0.02 solar masses of helium. And if you ask what is the velocity of this material, we find that the distribution of this material peaks at around 1,000 kilometers per second. That's around a factor of 10 lower than the typical ejecta velocity. So what that means is that if you want to detect any of this helium, you would need to wait around 100 days after the explosion when the supernova enters the nebular phase for any of this helium to show up as helium emission lines. But there currently is no realistic spectral modeling for detection of helium. So that's something that would be interesting to look at in the future. Okay, so our simulations can only go up to 20 minutes of physical time because a 3D hydrodynamical simulation is very expensive. And we want to know whether D62 will stay puffed up for the next million years. And so we map our 3D simulation back into the 1D stellar evolution code MESA and evolve it forward. And here, the colored tracks here show the evolution of our shocked donor models in the following 10 to 7 years. Okay, so the different colored points here label different ages. So we start off big and puffy of around 0.3 solar radii. Then the donor star undergoes Kelvin-Helmholtz contraction. And after roughly 10 to 7 years, it becomes a white dwarf again. But by then, it probably will have left the Milky Way. Okay. And the current observed location of D62 on the HR diagram is labeled here. So our models do kind of reproduce the large and puffy radius of D62. But at an inferred age of 10 to 5 years, our models are actually slightly more luminous than D62. So our future goal is to look at a wide range of parameter space to see whether we can explain D62 and other hypervelocity stars to see whether we can reproduce their big and puffy radius. And so to summarize, we find that during the interaction, roughly 0.01 to 0.02 solar masses of helium is stripped along with the ejecta, and with a typical velocity of 1,000 kilometers per second. And because the donor suffers a very strong shock, it then puffs up to of order 0.1 solar radii, and which allows us to detect them for the next 10 to 6 years. And thank you.
Is there any effect on nuclear energy as a result of the possible detonation that you can get?
Yeah, so you mean when the shock goes through
Yes.
the donor, is there any?
Yeah.
Okay, great question. So in this model, we find that the typical burning timescale is around 1,000 seconds. So that's too short for any nuclear burning to happen. But there is a suggestion that if you move to more massive donor stars, the density is higher, and there might be a hot spot roughly here as the shock goes through, which allows a strong helium detonation, where the heating timescale is shorter than the sound crossing time. So you get a burning front that moves faster than the sound speed.
That's interesting because it could add to the light, I guess.
Yeah. So we're currently trying to run more massive models, and actually last week I did have a preliminary model that shows that maybe this burning is really happening.
But if you add a sustained detonation, you'll destroy the donor star and you won't get a runaway, right? So
Yeah.
it's a dangerous game you're playing.
Interesting. Any questions, comments? It's like, that's a compliment, by the way, that because you explain things very well. Thank you to all the speakers today.
And that was kind of like very clear before saying like